We continue our discussion on solving differential equations with the solution of separation of variables. We already covered direct integration, and partial fraction expansion will come a bit later. So separation of variables deals with differential equations of the following form. dy dx is some function of x, f of x, times some function g of y, where we have a first order differential equation where it is possible to isolate it like this, and then it's equal to a function of x, our independent variable, times a function of our dependent variable. So for example, dy dx is equal to x times y minus 2. So we have a function f of x here, which is just equal to x, and we have g of y here, which is equal to y minus 2. So it's a function of x times a function of y. Now another example, let's see, t squared plus 3t plus 2 times dx dt is equal to 5 over x. Now it's not immediately obvious that this is of this form, but if we divide left and right by this term, we find that we have dx dt is 5 over x times 1 over t squared plus 3t plus 2. And again, we have separated it into a function of x, which is equal to 5 over x, and a function, first the function of the independent variable, which is f of t. Of course the letters don't matter, but I'll try to be consistent with this. T squared plus 3t plus 2 times the function of the dependent variable x. Here the dependent variable is x, here it was the independent variable, but I mix it up to show you that you can come across any form here. So we have the function g of the dependent variable and the function f of the independent variable like this. So we're looking at differential equations of that form. Let me just grab my piece of paper with the examples, which is not this piece of paper. Ah, there it is. Now, the book explains it in a certain way, which is what I would call the shorthand version of it. There's a bit of a longer discussion that I would like to include, but rest assured you only have to use the shorthand version that the book shows. But I want to have a complete overview of the mathematics here. If we start with this equation here, dy dx is equal to f of x times g of y, what we want to do is move everything of one variable to the left. So I move everything with the independent variable to the left and everything with the dependent variable to the right. And we end up with, the independent variable goes to the left, so I'll divide by g of y, and we have 1 over g of y times dy dx is equal to fx. Now, some books will also move this dx to the right. I will do that in the shorthand version, but I want to show the proper mathematics, well, a more complete version of the mathematics here. What we can do, if we've written this differential equation in this form, is on the left-hand side and the right-hand side, integrate with respect to x. So 1 over g of y times dy dx times dx is equal to the integral of fx dx. And now I want to apply which is in essence the substitution rule, where these terms dx cancel each other out. In essence, I'm using the substitution rule, and we get 1 over g of y dy is equal to fx dx. And if g and f are known, we can calculate this. And then we can solve it eventually to find y of x is something. All right, so starting with a differential equation like that ends up in having to integrate this function and this function. But you can see why it's called separation of variables, because we have separated it out into something where we only have y and something where we only have x. And we do that, in essence, that's doing this here as well, but I'll show you that in the shorthand version. All right, first an example. dy dx is x times y. So here we have a differential equation of this form where fx is simply x and gy is simply y. Let's make it even easier. Let's do it like this, where fx is not even x, it's just simply 1, and here we have our y. We'll move on to a slightly more complicated one, but let's take the simplest one to illustrate a certain point. Now we move everything with y to the left, so we get 1 over y dy dx is equal to 1, as we had 1 times y. We can integrate left and right. 1 over y dy dx is the integral of 1 dx, and we know what the integral of 1 dx is. It is equal to x plus c, and don't forget the integration constant here, because that is absolutely essential, as we have also seen in the previous discussions. Now if I integrate this, this is equivalent to 1 over y dy, apparently, so this is x plus 1. And the primitive function of 1 over y with respect to y is ln of the absolute value of y. Now we can add some integration constant. That is fine, but we don't have to. Because what would happen is that we would move that integration constant to the other side, is equal plus c minus c2, and that together, let's go for blue, that together I would simply call, well, if this was then c1, then this together I would call c, and I'd still end up with just one integration constant. So to make life a bit more easy, you only have to deal with the integration constant on one of the sides, and it's easier to pick the right hand side. So we end up with ln, the absolute value of y is equal to x plus c. Now I don't like this natural logarithm here, so I on the left hand side and the right hand side I take e to the power of ln y is equal to the power of x plus c. So e to the power of the whole left hand side is equal to e to the power of the whole right hand side. I know that the exponential function and the natural logarithm are each other's inverse functions, so I end up with y absolute is e to the power of x times e to the power of c. And this is the point where the book, this is left out in the book, and this is also left out in many explanations of separation of variables, because it adds a layer of complexity. Now I'm only going to do this layer of complexity once, and in the next videos I will leave this out, but this, I might add it, but you can do it the way the book does, but I want to explain it properly. Now, e to the power of c is always greater than 0. So let's call e to the power of c, I'll call that c3. If an absolute value is equal to something, and well, by the way, e to the power of x is also always positive, so we get c3 e to the power of x. We know that y is equal to some constant, that constant e to the power of x, or y is equal to minus that constant e to the power of x. And that is the way we remove these absolute values. So for positive values of C3, we get a solution, and for negative values of C3, we get a solution. If then also C3 equals 0 is a solution, which it is, because that will be the trivial solution, then we can just simply write, instead of writing, so y is C3 e to the power of x, or minus C3 e to the power of x, or 0, we can bulk this together and say y is equal to some integration constant e to the power of x, where this c is just simply any real number. So what is the main complexity here is we have to deal with this absolute value. We have e to the power of c, which we can write as some other coefficient. We could also call it a or b, it doesn't really matter. If we have that the positive value of y is equal to this, it can be the positive value or the negative value, but because it can also be 0, that is also a solution here. Because if y equals 0, then the derivative of y is also equal to 0. So the function where x is equal to 0 everywhere is also a solution. And that is what I mean by this. So we have positive values for C3 are solutions, negative values for C3 are solutions, and we have 0 to be a solution. And then we just simply write y is c e to the power of x with c in the set of rational numbers. And the shorthand version skips over this process here. We go immediately to that. That is just a simpler way of doing it. But I'd like to have, so I include two things which the typical explanations don't, is that I explain here that we use the substitution rule, and here I explain that how to deal with the absolute values. And in the next examples, I will also solve this by using a shorthand version where we leave out this part of the discussion and leave out this part of the discussion.